So today we're going to cover derivatives of inverse functions. Okay. So starting off, we're just going to do a quick review of inverse functions. So an inverse function exists if the function is 1-to-1. I might as well just put it next to it. Inverse functions exist if the function is 1-to-1. Okay. Which means that for every x, there's one y. For every y, there's one x. You don't have x equals 3, have y equals 4, and y equals 8. And you don't have x equals 4 equals, well, x equals 4 is connected to y equals 8, and x equals 7 is connected to y equals 8. So each of them have just one y value. Every x value corresponds to one y value, and every y value corresponds to one x value. Or another way you could look at this is to say that it's strictly monotonic, which means it's strictly increasing or it's strictly decreasing across the entire function. On the entire domain. Okay, so if it's monotonic, it's automatically 1-to-1. Okay, so let's say, just for the sake of argument, we decide to prove the second one. Okay, so let's say it's strictly monotonic. Okay, so that means that it's either increasing or it's decreasing. We'll write some, let's say, a random graph that happens to be increasing. Okay, so that means, if f of x1 equals f of x2, that means if two y's are equal, then that means the two x values have to be equal. Then x1 equals x2. Okay, so let's say that's our x1. Okay, let's say this is our f of x1. Okay, so if f of x1 and f of x2 are equal, then that means x1 and x2 has to be equal, since they're both on the same point. Okay. Now that means the contrapositive is also true. Means if x1 doesn't equal x2, then f of x1 doesn't equal f of x2. Is also true. Okay, so if we were to graph that one, move that up a little bit. So you have that same random graph. Okay, so let's say this is our x1, and this is our f of x1. Okay, so we know x1 and x2 aren't equal, so that means x2 has to be somewhere here, or it could be on the other side. We'll just put it there just because. Okay, so that means our f of x2 isn't equal to f of x1. Okay, so since we know that x1 and x2 aren't equal, then that means that f of x1 is less than f of x2, or f of x1 is greater than f of x2. Okay, either way, they're not equal, which means that for every x you have one y, and for every y you have one x. F of x1 doesn't equal f of x2. So f of x is 1 to 1. All right, any questions on that one? All right, leave that up for a few seconds. All right. Okay, so let's say just a few quick examples. Let's say if you have some x and y here. Okay, so you have -2, -1, 0, 1, and 2. Let's clean that one up a little bit. There we go. Let's say for our f of x, we had 7, 9, 15, 18, and 24. Okay. So we can actually say this one's 1 to 1 because every x has one y, so -2 only has one value. -1 only has one value. Same with 0, 1, and 2. They only have one y value. So we go to the y values. 7, y equals 7 only has one x value. You don't see y equals 7 equal anything else. Same thing with 9, 15, 18, and 24. So you can see there that it's 1 to 1. Uh-oh. Clean that up. Since every x has one y, and every y has one x. All right, so if we had, let's say, another quick example. So we have our x, we have our f of x. And again, let's go -2, -1, 0, 1, and 2. Let's say 7, 5, 4, 5, and 3. Okay. Now this one actually is still a function. because every x has one y. But it's not 1 to 1 because every y has more than, well, not every y has just one x. See, y equals 5 has -1 and it has 1. Okay? So you can only have one going both ways. So this one would pass the vertical line test, but not the horizontal line test. Is a function since every x has one y, but not 1 to 1, since y equals 5, clean that up, corresponds to two x values. All right, so any questions on that one? All right. And for a quick last example, so we have our x, we have our f of x, say -2, -1, 0, 1, and let's say -2, 9. Okay, so this one isn't even a function because you can't have x equals -2, have a y value of 4, and a y value of 9. So this one doesn't even qualify for a function, so you know it's not 1 to 1. All right, so any questions on those? All right. Okay. Okay. Say, for example, if you wanted to identify the function that has an inverse. Okay, so for A, let's say f of x equals x to the third plus x minus 1. And for B, let's say f of x equals x to the third minus x plus 1. Okay, and a quick note. We know that if the slope is always positive for the entire function, then that's how we can tell if it's monotonic. So if it's either always positive or always negative, then we'll know. So if the derivative is strictly positive, or strictly negative, for the entire domain, then it's 1 to 1. 1 to 1. Okay, so all we have to do is just find the derivative and see if it's always positive or always negative. Okay, so for A, since we know that f of x is equal to x to the third plus x minus 1, or f prime of x is equal to 3x squared plus 1. Okay, so that means no matter what you plug in for x in your derivative, it's always going to be positive. If you plug in any negative number, of course negative times negative will make that positive. Since it's plus 1, it's always going to increase. So you know the entire graph is going to increase. Okay, so if we make a quick little graph of this one so you can get a visual, and it kind of looks like that, give or take. And it crosses at -1, and here crosses a little bit just before 1. All right, so it kind of looks like that. So you know across the entire graph, the slope is increasing. Okay, now for B, we have f of x equals x to the third minus x plus 1. So f prime of x is equal to 3x squared minus 1. Okay, so we know if we plug in 0, you can have a negative number, but if you plug in 1, you're going to have a positive number. So you can't have a positive slope and a negative slope because you know at some point it's going to go down. So we know just because of that, we know it's not 1-to-1. You have both positive and negative slopes. Well, derivatives technically. Even though it is slopes, we'll just say derivatives. All right, so any questions there? All right, leave that up for a few seconds. Excuse me. All right. Okay, so just a quick steps to find the inverse equation. Okay, so 1, if necessary, you can kind of see if it's monotonic if you have to test for it. Excuse me. But in most cases, you won't have to. And that is used just the previous example. That's how you would do that, just to find out if you have positive and negative slopes. And that's if necessary. Okay. So the second is you're going to replace f of x with y. And then you're going to interchange the x and y's. And you're going to make y's become x's and x's become y's. Okay. Then you're going to solve for y and then replace it with f inverse of x. Okay. And you can always double check your answer because if you have the function of the inverse, it should equal x. the inverse of the function g equal x. Okay, so they kind of cancel each other out, I guess you could say. Not really, but you should get that result. All right, so let's do a quick example. And I should be able to do it on this. I'll do it on another sheet. All right, no, it's still writing. I'll leave it up there for a few more seconds. All right. Okay, so let's say, for example, if we wanted to find the inverse, function of, let's say, f of x equals square root of 2x minus 3. Go clean that up some. Okay, so we're pretty much going to assume that it's 1-to-1. But in case you want to check, first step. Okay, so f of x equals, we can actually rewrite it to be 2x minus 3 to the 1/2 power. Okay, which means our derivative, we're going to bring down that 1/2. Of 2x minus 3, subtract 1 from here. 1/2 minus 1 is negative 1/2. Times the derivative of what's inside, which is just 2. Okay, so those two cancel each other out. So our derivative is going to equal 1 over the square root of 2x minus 3. Okay, which means our domain needs everything, or your complete radicand, to be greater than or equal to 0. Okay, if it's less than 0, then you're going into negative square roots, and that's when you have to deal with complex numbers, and we're not dealing with complex, we're just dealing with real numbers. Okay, so we know the square root, 2x minus 3, has to be greater than or equal to 0. Which means if we square both sides, 2x minus 3 has to be greater than or equal to 0. Add 3 to both sides, 2x has to be greater than or equal to 3. Divide both sides by 2, x has to be greater than or equal to 3 over 2. Which means our domain for this function, or for this, I guess you could say this function, is from 3 over 2 to infinity. Okay, so we already know everything from 3 over 2 to infinity would give you a positive number. If not, then it wouldn't be in the domain. So we know the domain is actually going to be positive. Well, the derivative is going to be positive for the entire domain. Okay. So we know it's 1-to-1. Like I said, we didn't have to check it, but that was just one of the ways to check it. Okay, so your second step, well, actually second and third step, so we're going to interchange, change our f of x to y. Y equals the square root of 2x minus 3. Then we're going to interchange our x and y. So we'll make that x equals the square root of 2y minus 3. And now we're going to solve for y. Okay, so if we squared both sides, we'd have x squared equals 2y minus 3. If we add 3 to both sides here, we have x squared plus 3 equals 2y. And if we divide both sides by 2, we end up with y equals x squared plus 3 divided by 2.
There was a name for that strategy. What was that called?
Oh, we're just solving for the inverse.
Okay.
Yep, solving for the inverse of the function.
I thought someone had a great.
It might have. Sometimes they have multiple names to them. I guess it depends on who writes that particular book. Okay. So remember our fourth step, we're going to replace y with f inverse. So f inverse of x is equal to x squared plus 3 over 2. Okay. And then we can just go ahead and check it. Don't have to, but we'll check it anyway. Okay, so f of f inverse should equal x if we did everything correctly. Okay, so f of f inverse is x squared plus 3 over 2. So we can replace that f inverse as x squared plus 3 over 2. Okay, so since our f of x is square root of 2x minus 3, we just replace the x with our inverse. So that's the square root of 2 times x squared plus 3 over 2 minus 3. Okay. So those 2's cancel each other out, so we can go ahead and get rid of those. That leaves us with square root of x squared plus 3 minus 3, where those 2 cancel each other out. So you get the square root of x squared, which the square root and the square cancels each other out, so you end up with x. So it passed our check, so now you have the right inverse. All right, so any questions on that one? All right. And it also works if you decide to f inverse of f of x equals x. But we only have to really do one. All right. Okay, so now we're going to actually go to the formula to find the derivative of the inverse. Oops. Okay, so if f of x has an inverse, function f inverse of x, then the derivative of that inverse is equal to 1 over the derivative of the inverse. Be careful between the inverse sign and the derivative slashes. There's a lot of little marks all over the place. All right, and that's going to cut off in about a minute, so I might as well